Do you know who this is? How about now? Well, you guessed it. That's Alien Newton. I mean, of course it is. Who else would it be? You okay, Alien Newton? That's good. He's just a little bit dramatic. Okay, well, let's talk about derivatives. Maybe I can't tell you exactly why he was crazy about derivatives, but I can tell you what they are. A derivative is the graph of any given function's slope, so the graph of the rate of change. It's easy enough on a linear function. Their slope remains constant and can be pulled exactly from the equation. But it gets a little bit more complicated when you get to nonlinear functions. There are two ways to find the rate of change of a function. One is the secant line, a line which goes through 2 points and will only give the average. That one is pretty easy to find, but isn't what we are looking for. We want the exact slope of a function at every individual point. This brings us to tangent lines. They only touch the function at one point and will yield an exact slope. But how do we solve for this? Rise over run will, well, yield 0 over 0. Before we solve this issue, we need to sidetrack a bit to what a limit is, which is just a fancy way of saying the values that something is approaching rather than what it actually is. For example, if we have this function, which is smooth except for one little jump to an unspecified point f of p at x value p, the limit as the function approaches p is still going to be equal to 10. It is all about the value something is approaching. If we pretend we can't see the value of the function at point p, it seems as though the function will continue to be equal to 10. We write this as the limit of function f of x as x approaches p is equal to 10. There are a few more rules and technicalities associated with limits, but to keep it simple, let's jump back to where we left off. What can we do to find the slope of a tangent line? Well, bring back the graph. What we can do is start with the secant line with points f of b and f of a. Next, let's rewrite f of b as f of a plus some value, calling this value h. And now, when we write out the slope formula, we get something that looks a little different. Let's simplify it a bit. Now this is where it gets pretty fun. We want to gradually decrease the value of h, bringing the 2 points of our secant line closer and closer, until h equals 0 and we have not a secant line, but a tangent line. So now we can rewrite the slope formula. But hold on, this just turns into the faulty 0 over 0 we originally found with the tangent line. But not if we use limits. Bring back the slope formula. We want h to get as close as possible to without actually becoming 0. So we want the limit of f of a plus h minus f of a all over h as h approaches 0. We won't solve for a specific function right now, but this limit will let us solve for the slope of almost any function at one point with a negligible error due to estimation. There's no way for us to calculate it if the difference between the 2 points is actually 0, but we can approach 0 closer and closer and closer using a limit, yielding the function of almost any derivative your heart could desire. And that is how some old, crazy math people found out a way to truly find instantaneous slope.